All right, welcome everyone to another deep dive. Today we're diving into something kind of meta, We're talking about AI, but specifically how AI is being used to change how we design other AI chips, those field programmable gate arrays or FPGAs that everyone's been talking about.
Yeah, it's like AI inception, right?
Yeah,
Designing the tools that'll design even smarter tools.
exactly. And you hear all the time about AI this and AI that, but you rarely hear people talk about the data that fuels it all. So that's what we're going to be digging into today, the absolute importance of good, clean data when it comes to this whole AI-driven design revolution, especially for FPGAs.
It's absolutely foundational. You could have the most sophisticated algorithms in the world,
Yeah,
but if you're feeding them garbage data, you're going to get garbage results.
makes sense. So where are we seeing AI making the biggest impact in the FPGA design process? What are the hot spots, so to speak?
Well, we're seeing a lot of exciting work in high-level synthesis that's basically taking a more abstract description of what you want your hardware to do and automatically generating the nitty-gritty details of the actual circuits. Then there's logic synthesis. That's where we tailor the design to a specific FPGA chip, optimizing for things like speed, power, and area. Placement and routing is another area where AI is proving incredibly valuable. That's all about figuring out the most efficient physical arrangement of components on the chip. And of course, we can't forget about predicting the power and performance of these chips early on, which is crucial for making smart design choices from the get-go.
Right, because if you design this amazing chip, but it ends up drawing way too much power, that's kind of a deal breaker in a lot of applications.
Totally. And we'll also touch on how AI is starting to play a role in enhancing the security of those hardware security modules built on FPGAs. But first, let's break down high-level synthesis, or HLS, a bit more.
Okay, so for those who might not be totally familiar with HLS, can you just give us a quick overview?
Sure. So traditionally, designing hardware for FPGAs involves writing code in these really low-level hardware description languages like Verilog or VHDL. But HLS lets you describe your design in higher-level languages that are more familiar to software developers like C or C++.
So it makes the design process more accessible to a wider range of engineers.
Exactly, and potentially more efficient. The HLS tool then takes care of translating that high-level description into the detailed Verilog or VHDL code that defines the actual hardware circuits on the FPGA. This has the potential to significantly speed up the design process and reduce those pesky verification times.
Sounds like a win-win.
Yeah.
So where does AI come in?
Well, one of the coolest things about HLS is that it gives you a lot of flexibility in how your high-level code gets synthesized into actual hardware. There are all sorts of options and directives you can use to tweak how the circuits are implemented, which can have a big impact on things like the speed, power consumption, and the amount of chip resources your design uses.
So it's like having a recipe, but you can substitute ingredients and adjust the cooking time to get different outcomes.
That's a great analogy. The problem is that the number of possible configurations can be absolutely overwhelming. It quickly becomes impossible for a human designer to explore every option manually. That's where AI comes in. It can be trained to navigate this complex design space and find those optimal settings that meet your specific performance goals.
Makes sense. So what kind of data does this AI need to become a master chef, so to speak? What ingredients go into its training?
Well, first we need examples of those initial high-level descriptions in languages like C or C++.
Okay, the starting point of the design.
Exactly. Then we need the resulting Verilog or VHDL code that gets generated by the HLS tool when different combinations of those synthesis options and directives are used.
So it's not just the input and output, but also the actual synthesis process that was used.
Right, that's crucial. The AI needs to learn the relationships between those synthesis settings and the resulting hardware. And of course, we need the performance metrics of the generated hardware, things like latency, throughput, how fast the clock can run, and how quickly it can start processing new data.
Basically all the vital statistics of the circuits.
Exactly. And we also need to know how much of the FPGA's resources each version consumes. How many lookup tables, flip-flops, memory blocks, and so on. And ideally, power consumption estimates as well, whether they come directly from the HLS tool or from additional analysis.
So it's like a detailed performance review for each version of the hardware.
Right. For more advanced AI models, we might even feed in those intermediate steps of the HLS process, like the intermediate representation or IR code, which is kind of a more abstract version of the design before it becomes Verilog or VHDL.
It sounds like a ton of data for each design.
It can be, and that's one of the big challenges here. This design space is enormous, and it just keeps growing as HLS tools become more sophisticated. That's why having AI that can quickly sift through this vast sea of possibilities and guide us toward optimal solutions is so incredibly valuable.
Makes perfect sense. So let's move on to the next stage in the design process, logic synthesis. Can you give us a quick rundown of what happens there?
Sure. So you've got your high-level description of the hardware, usually in what's called register transfer level, or RTL, Verilog, or VHDL. Logic synthesis takes that RTL description and maps it to a specific FPGA. It figures out exactly how to implement those high-level functions using the basic building blocks that are available on that particular chip.
So it's like taking a blueprint and figuring out how to actually build it using the materials you have on hand.
Exactly. And there are, of course, multiple ways to do this. The goal is to find the most efficient implementation, one that meets your performance targets, while minimizing the area used on the chip and keeping power consumption in check.
And again, AI is being used to navigate this process.
That's right. Instead of trying every possible combination of logic synthesis settings, we can train AI models to predict the outcomes based on the RCL code and the specifics of the target FPGA.
So it's like having an experienced engineer who can look at your code and say, based on what I've seen before, if you use these settings, you'll probably end up with a design that's about this fast and uses about this much area on the chip.
Yeah, that's the idea. To do that, though, the AI needs the right data to learn from. We start with the RTL level HDLs, of course.
Right.
But critically, we also need very detailed specs about the FPGA's architecture. Things like the types and number of logic blocks, how they're interconnected, and their timing characteristics.
So the AI needs to know the strengths and weaknesses of the hardware it's designing for.
Exactly. We also need to feed it the specific parameters and scripts that were used to control the logic synthesis tool. Things like what optimization goals we're aiming for and how much effort we want the tool to expend in trying different approaches.
And of course, we need the results of the synthesis process itself, those net lists that define how the circuits are connected, along with the timing reports that tell us about critical path delays and the area reports that break down how many of each type of logic element were used.
Oh, and the power consumption estimates too, all that good stuff. Basically, we're giving the AI a comprehensive view of the entire logic synthesis process, the input, the output, the tools used, and the settings that were chosen. By learning from this data, it can start to make predictions about how different design choices will impact the final synthesized circuits.
This is really fascinating stuff. So we've got our design synthesized. We know how it's going to be implemented on a specific FPGA. What's next?
Now we get to the nitty-gritty of placing and routing those logic elements on the actual FPGA fabric. This is a really tricky part of the design process because it has such a huge impact on the performance, power consumption, and even the feasibility of the entire design. Well, imagine you've got all these logic blocks, hundreds, thousands, maybe even millions of them that need to be arranged on the chip. And then you have to find physical paths to connect them all according to your netlist, navigating through a maze of predefined routing resources.
Sounds like a giant jigsaw puzzle with a ton of extra constraints.
You could say that.
Yeah.
If you place components poorly, you might end up with long wires that slow down your circuit or create congestion that makes it impossible to route certain connections.
And I imagine a poorly routed design is going to use more power, too.
Absolutely. So this is where AI can really shine. Deep learning algorithms, in particular, have shown a lot of promise in predicting readability, optimizing placement, and even guiding the routing process itself.
Can you give us some more detail on that? How is AI actually being used in these steps?
Sure. One important application is using AI to predict early on whether a given placement is likely to be routable. Before you spend a ton of time trying to route it and find out you've hit a dead end.
That would save a lot of headaches. How does that work?
Well, you can train an AI model on tons of data from previous designs, the placement information, and whether those designs were successfully routed. The AI can then learn to spot patterns that are indicative of potential routing problems. So if you feed it your new placement, it can give you an early warning if it thinks you're heading for trouble.
Very cool. And you said AI can also be used to optimize the placement itself.
Exactly. The goal here is to find placements that minimize wire length and congestion, which generally leads to better performance and lower power consumption. AI algorithms can explore a vast number of placement possibilities much faster than traditional methods and can often come up with solutions that a human engineer might never have considered.
So it's not just about avoiding bad placements, but actually finding the best ones.
Right. And there's also active research on using AI to guide the routing process itself. Techniques like reinforcement learning are being explored to discover more efficient paths through that complex routing maze on the FPGA.
Reinforcement learning, I know that's been used for things like game playing AI. How does it apply to routing?
It's a bit like teaching an AI to play a game where the goal is to find the shortest and least congested path for each connection. The AI gets rewarded for good routing choices and penalized for bad ones. And over time, it learns to become a really good router.
That's amazing. So what kind of data do we need to train these placement and routing AIs?
Well, we obviously need the net list. That's our connectivity map. And then we need a really detailed description of the target FPGA's architecture, the arrangement of the logic blocks, the routing channels, the programmable switches, everything.
So like giving the AI a 3D model of the chip it's working with.
Precisely. Then we need the results of the placement and routing process, the actual physical locations of each component, and the paths that were chosen for the connections. And of course, the performance metrics, the total wire length, the critical path delay, the amount of congestion in different areas.
It sounds like we're building up a detailed history of successful and unsuccessful placements and routings, and then using that to train the AI.
Exactly. And we can also extract features directly from the design itself. Things like the locations and types of logic blocks, the available routing resources in different areas, timing constraints, and power requirements. All this information can be used to train the AI to make smarter decisions about placement and routing.
This is really mind-blowing stuff. It seems like AI is becoming an integral part of every aspect of FPGA design. But even with these powerful tools, wouldn't it be great if we could predict how well a design is going to perform before we even get to the placement and routing stage?
Absolutely. That brings us to another really important application of AI in this field, power and performance prediction. If we can get an accurate estimate of things like speed, power consumption, and resource utilization early in the design process, it can save us a ton of time and effort down the line.
I can imagine. It would let you catch potential problems early on before you've invested a lot of time in a design that might not be feasible.
Exactly. And it can help you make more informed decisions about the overall architecture of your design and how you choose to implement it. Now, AI is particularly good at this kind of prediction because it can learn those complex relationships between the design parameters and the resulting performance characteristics relationships that might be really hard to capture with traditional methods.
So what kind of data do we feed these predictive AI models?
It's a pretty wide range, really. We start with the high-level specifications of the design, what it's supposed to do. Then we incorporate information about the HLS directives and synthesis options that were used, since those have a big impact on the final hardware. The HDLs at different stages of the design process can provide valuable clues, too, even before we get to the fully synthesized netlist.
So we're giving the AI as much context as possible about the design and how it's being implemented.
Right. And we also feed it data from those resource utilization reports, timing reports, and power analysis reports that we get from the various design tools. The intended application of the hardware can also be a factor, as can simple counts of things like arithmetic operators, input-output pins, registers, and memory blocks.
It sounds like we're trying to give the AI a holistic view of the design, not just focusing on one specific aspect.
That's exactly right.
Yeah.
And the more information we can give it, the better its predictions are likely to be. And I should mention that there's a really cool open source resource called the HLS dataset that was created specifically for this kind of work. It contains a bunch of HLSC benchmarks, synthesis directives, and the resulting performance and resource utilization metrics, which is incredibly helpful for training these predictive models.
Shared resources like that are so important for advancing the field. Now, we've talked about using AI to optimize the performance and efficiency of FPGAs, but what about security?
Ah, yes, a crucial aspect. FPGAs are increasingly being used in hardware security modules, or HSMs, which are basically specialized pieces of hardware designed to protect sensitive data and operations.
So things like encryption keys, financial transactions, that sort of thing?
Exactly. And AI can be used to make these FPGA-based HSMs even more secure. One really interesting application is real-time threat detection. You can train AI models to analyze the behavior of the hardware and spot patterns that might indicate a security breach or malicious activity.
So it's like having an AI watchdog constantly monitoring the system for anything suspicious.
Yeah, that's a great way to put it. But to do this effectively, the AI needs the right kind of data to learn from. We need the detailed design specs of the HSM itself, the HDL code that implements the cryptographic algorithms, the secure communication protocols, and any tamper-resistant features.
So basically giving the AI a blueprint of the security system it's supposed to be protecting.
Right. But we also need data on the types of security threats that might target FPGAs. This could include things like recordings of side-channel attacks, where an attacker tries to extract secrets by analyzing things like power consumption or electromagnetic emissions.
So the AI needs to know what to look for in terms of suspicious activity.
Exactly. We also need data on the normal behavior of the HSM, so the AI can learn to distinguish between benign and malicious activity. The specifics of the cryptographic algorithms being used are important too, as well as any data related to secure software and firmware updates.
It sounds like we're building up a whole library of knowledge about potential threats and how to defend against them, and then using that to train the AI to be a more effective security guard.
You got it. Now, we've talked about all these different types of data that are needed for AI-driven FPGA design. But where does this data actually come from?
That's the big question, right? Without good data, all these fancy AI algorithms are useless.
Exactly. Fortunately, there are some really great resources out there. We're seeing a growing number of publicly available datasets and benchmark suites specifically designed for this area.
Can you give us some examples?
Absolutely. One is the HLS dataset we talked about earlier, which is great for AI-assisted HLS design. Another one is the ML4Axel dataset, which includes data from both FPGA and ASIC design flows, which are the chips you find in things like your smartphone.
So it covers a broader range of chip design applications.
Exactly. Then there's Koyos 2.0, which is specifically for deep learning acceleration on FPGAs. It's got a bunch of Verilog and BLIF net lists for different deep learning network architectures.
So it's tailored to a specific application area, which is cool. Any others?
Yep, there are several more. Raise Bench focuses on the resource efficiency of HDL code that's actually generated by large language models, which is pretty cutting edge. Spectre is an OpenCL benchmark suite with a bunch of tunable parameters, so you can generate tons of unique design variations and collect a lot of data that way.
So it's kind of like a data generation playground for AI research?
Yeah, you could say that. For high-performance computing applications, there's the HPCC FPGA suite, which is based on the standard HPCC benchmark suite. And then there's PivPav, which is an open-source tool with a database of digital circuits and a benchmarking framework.
So there are already quite a few publicly available resources out there, which is great news. And we also talked about those data sets that are specifically focused on Verilog and VHDL code.
Right. Those are really important for training AI to understand, generate, and manipulate those hardware description languages. There's the Kaggle Verilog dataset, which has Verilog programs with intentionally introduced errors, which is great for training AI to do things like code correction.
So it's like a training ground for an AI debugger.
Exactly. Then there's Verilog GitHub. There's a huge collection of Verilog code scraped from GitHub, a gold mine for code analysis and pattern recognition. i.e. Dataport has some HDL datasets for security applications, like detecting hardware trojans. And the ZF Turbo NN Digit Detector repository has Verilog code for a neural network implemented on an FPGA.
That's really cool. So it seems like there's no shortage of data out there for these AI applications in FPGA design. But what if you're working on something really specialized and you just can't find the data you need?
That's where synthetic data generation comes in. It's basically creating artificial data that has the same statistical properties and characteristics as real data, but it's generated using computer simulations or other techniques.
So it's like creating your own custom data set when you can't find what you need out in the wild.
Exactly. You can do things like simulate FPGA designs under a wide range of conditions, run automated design space exploration to generate tons of different configurations, or even use AI itself to generate synthetic data using techniques like generative adversarial networks, or GNs.
So we can use AI to create data to train other AI models. That's pretty meta.
It is, and it can be incredibly powerful when you're dealing with data scarcity or privacy concerns. Now, it's worth mentioning that the companies that make FPGAs and those electronic design automation or EDA tools, they have a ton of data from their users' designs.
I bet they do, but I'm guessing they don't share that data very freely, right?
Yeah, that data is usually pretty tightly guarded. It's a valuable asset for them, and they're concerned about protecting their intellectual property. But it is interesting to think about all the potential applications for AI if we had access to those massive data sets.
For sure. So even with all these data resources that are out there, what are some of the big challenges that researchers and developers face when it comes to getting the data they need for AI in FPGA design?
Well, as we've touched on, data scarcity is a big one, especially for those cutting-edge applications or for really specific types of FPGAs. Intellectual property concerns are another hurdle. Companies are often reluctant to share their design data because it could give competitors an advantage. And the complexity of hardware design itself makes it tricky to capture all that expert knowledge in a form that AI can easily learn from.
Right. It's not always easy to translate human expertise into something that an algorithm can understand.
Exactly. And then there's the issue of data heterogeneity. All this data comes from different sources and different formats, and it often needs to be cleaned, normalized, and transformed before it can be used to train AI models. And all this data processing can be really time-consuming and expensive.
So it's not just about finding the data, it's about making it usable.
Precisely. And then there's the lack of standardized data formats and exchange protocols, which makes it harder to share and combine data from different sources.
It sounds like there are still a lot of obstacles to overcome. But even when we do have a decent amount of data, are there ways to make it go further, to squeeze more learning out of it, so to speak?
Absolutely. That's where data augmentation comes in. It's a way to artificially increase the size and diversity of your data set by creating variations of the existing data.
So it's like making your data work harder for you.
Yeah, exactly. For example, with HDL code, you could make minor changes to the syntax that don't affect the functionality of the code. Or you could do things like refactoring the code, breaking it down into smaller modules, or rearranging things a bit.
So it's kind of like showing the AI different ways of expressing the same idea.
Right. And with numerical data, you can add a bit of random noise or use techniques like interpolation and extrapolation to create new data points. For layout information, you can make small changes to the placement of components, but you have to be careful not to create designs that are physically impossible to implement.
It sounds like a balancing act between creating variations that are realistic and useful, but not so wild that they confuse the AI.
That's a great way to put it.
Yeah.
And there's even potential to use AI itself to generate new data using those generative models we talked about earlier. But that's still an area that needs more research. The key takeaway is that data augmentation can be a really powerful tool for stretching your data further, but you have to do it carefully and thoughtfully.
Makes sense. So once we have our data, whether it's real or synthetic, and we've augmented it to our heart's content, what's next?
Well, now we need to get it into a format that our AI algorithms can actually understand and learn from. FPGA design data comes in all sorts of different formats: text-based HDL code, net lists, numerical performance metrics, layout information, EDA tool reports. It's a real mixed bag.
So we need to do some data wrangling before we can unleash the AI.
That's right. For text data, like HDL code and reports, we often need to do things like parsing and feature extraction. This might involve using techniques from natural language processing or regular expressions to pull out the relevant information.
So we're basically teaching the AI how to read and understand those technical documents.
Exactly. And we also need to do data cleaning to deal with missing values, outliers, and inconsistencies. Numerical features often need to be normalized and scaled so they don't throw off the AI's learning process.
So making sure all the data is on the same playing field, so to speak.
Right. And then there's encoding categorical variables, things like the type of FPGA or the synthesis tool that was used. And sometimes we need to apply mathematical transformations to the data to improve its distribution.
So it's a lot of pre-processing work to get the data ready for prime time?
It is. And when you're dealing with really large data sets, you also need to think about creating efficient data pipelines to load and process all that information. There's a whole field unto itself.
Well, this has been an incredible journey through the world of AI-driven FPGA design. We've covered so much ground: the different applications of AI, the types of data that are needed, the sources of that data, the challenges in acquiring it, the techniques for augmentation, and the importance of pre-processing. It's clear that data is the lifeblood of this entire field.
I completely agree. Without good data, all those amazing AI algorithms are just spinning their wheels. And as AI and FPGA technology continue to evolve, the role of data is only going to become more and more important.
Absolutely. So as we wrap up, I'd like to leave our listeners with a question to ponder. As AI becomes more powerful and FPGAs become more capable, how do you think the relationship between hardware designers and data scientists will need to evolve? What new skills and ways of thinking will be needed to fully harness the power of this incredible synergy? That's something to think about as we all navigate this exciting new era of intelligent hardware design. Thanks for joining us.